Welcome to my channel once again. We will continue with electrochemistry. Here we will study about Tafel and Butler-Volmer equations. These come under electrode kinetics or kinetics of electrode processes. Many students find these topics difficult to grasp. Before going directly into these, just recollect what you know about electrodes and electrode reactions. The word electrochemistry derives from the terms electricity and chemistry. It applies to scientific discipline as well as a sector of industry. In short, it is the chemical phenomena that are coupled with the reciprocal exchange of electric energy. In a galvanic cell, electricity is produced, and in an electrolytic cell, electricity is consumed. You are familiar with different types of electrodes. The simplest among these is the metal-ion electrode. Such an electrode can be constructed easily by putting a metal rod into a solution containing its own ions. For example, a zinc rod dipped in zinc sulfate solution or a silver rod dipped in silver nitrate solution. Now let us construct a zinc electrode. For that, I am dipping a zinc rod into zinc sulfate solution taken in a beaker. Just look at the figure. This setup will generate a potential which we call as the electrode potential. Now let us see how the potential is generated. You know, zinc has a tendency to give away electrons. So zinc atoms start dissolving into solution, leaving the electrons on the zinc electrode. As a result, negative charge accumulates on zinc rod. At the same time, there occurs an increased positive charge in the solution. Initially, before placing the zinc electrode, the number of positive ions and number of negative ions are same in the solution. Since the more zinc ions dissolve into the solution, there is an accumulation of positive charge. Similarly, zinc atoms are removed as zinc ions. There is an increased negative charge on the zinc rod. After a while, the zinc ions come near the metal rod and surrounds it. As a result, a charge separation occurs at the metal solution interface. Thus, a potential is generated at the interface. It is more or less like a capacitor. Chemically, the zinc undergoes oxidation. That is, zinc giving zinc 2 plus 2 electron. Soon an equilibrium will be established by the occurrence of the reverse process. The zinc ions from the solution go to zinc rod, take electrons and get deposited as zinc metal. The potential developed under this condition is the electrode potential. As you know, electrode potentials are based on reduction processes and hence called reduction potentials. If an atom has a higher tendency to lose electron than to accept, its electrode potential will be negative and vice versa. The reduction potential is a measure of the tendency to gain electrons. Oxidation potential of an electrode is numerically equal to the reduction potential but of opposite sign. If the electrolyte solution is of unit activity and if the metal electrode is in the pure state, the potential developed is called standard electrode potential. It is usually measured at 25 degrees Celsius by combining with a standard hydrogen electrode whose potential is taken as 0. For example, the standard electrode potential of zinc is minus 0.76 volts. Now let me construct a copper electrode. For that, I am dipping a copper rod into copper sulfate solution. Copper has a tendency to accept electrons rather than to release electrons. So copper ions from solution moves towards the electrode and get electronated. Electronation means addition of electron. Thus, a reduction process occurs. That is, Cu2 plus 2 electrons giving Cu. Since copper has a higher tendency to accept electrons, the standard electrode potential of copper is positive. And for copper, it is plus 0.34 volts. The electrode where oxidation or de-electronation occurs is called anode, and electron where electronation or reduction take place is called cathode. If we connect these electrodes externally by a conductor and internally by a salt bridge, we get the simplest galvanic cell, that is the Daniell cell. In a galvanic cell, anode is negative and cathode is positive. On the other hand, in an electrolytic cell, the anode is positive and the cathode is negative. Electrolytic cell produces chemical energy by passage of current. In our discussion, we are more interested in electrolytic cells. Of course, you have studied all these topics in lower classes. I mentioned these only to fresh up your memory. An electrode is a special kind of surface. The special kind of process that occurs there is transfer of electrons. Consider an electrode immersed in an electrolyte solution. Look at the expanded view of the small portion of the interface. We can observe an electrical double layer between the solid and liquid phases. In this case, the electrode is assumed to be positively charged. Now the double layer consists of a sheet of positive charge and a sheet of negative charge next to it in solution. It can occur in the reverse manner also. That is, negative charge in the electrode and a positive charge in the solution. It is more or less like a capacitor which has two plates of charges separated by some distance. There are different models for interpreting this situation. In solution, the ions are believed to be solvated. Generally, positive ions are heavily solvated because of its smaller size. Here we take water as the solvent. Look at the figure. The solvated anions arrange themselves along the electrode surface with their solvation sphere. So there is a layer of water molecules next to the electrode surface. Thus the array of negative ions is cushioned from the electrode surface by the solvent molecules. On the electrode, there is an excess of positive charge, and next to the interface, there is an excess of negative charge. But as we move away from the interface into the bulk of the solution, this accumulation of charge disappears and the ions get evenly distributed. Now let me draw a line through the ions which are closest to the electrode surface. It makes a boundary. The region within this boundary is called the Helmholtz layer. This region is the compact part of the double layer. The line represents the outer Helmholtz plane, usually written as OHP. Sometimes the ions in solution may go near the electrode without the solvation sphere. A line passing through the center of such ions is called inner Helmholtz plane. But another model is there, and which is known as the Gouy-Chapman model. This model rejected the rigid nature of the double layer and suggested a diffuse layer because of the thermal motion which causes disordering. A third model also is there, which combine both these models. It is the Stern model. In Stern model, the ions closest to the electrode are constrained to the rigid Helmholtz plane, while outside that plane, the ions are dispersed as Gouy-Chapman model. The figure shows such a model. Because of the charge separation, a potential will be developed. In the figure, phi m is the electrode potential at the electrode surface and phi s is that in the bulk of the solution. In the bulk of the solution, it is almost zero. The potential decreases sharply within the solution up to OHP, that is outer Helmholtz plane, and then decreases exponentially. All of us frequently use the word electric current. Actually, what is current? Ampere in 1820 defined current as the overall movement of charges in a conductor. More specifically, the movement of charged species. This corresponds to the charge flow rate or charge flux. Consider a cylinder as shown here. Imagine that electricity is flowing through it. Now we can take a crude analogy of water flowing in a pipe. Suppose that a charge dq crosses the plane of area A at x is equal to 0 in a time interval dt. Then the magnitude of electric current will be dq upon dt. Now the sign of the current is defined by the orientation of the normal vector, and the unit of current is ampere. It is 1 coulomb per second. Now we define another important quantity called current density. It is represented by the lowercase letter I. When a current flow across and at right angles to a surface of area A, as shown in the figure, the current density will be the quotient of I, that is the current, and A, area of cross section. It is measured in ampere per square meter. Like the pressure exerted by flowing water in a pipe, if a current I is flowing across the plane at x is equal to 0, the same current I will be flowing across every other parallel planes in the tube. Moreover, identical current I must also be passing into and out of the conductor along the wires, though the current densities in these wires will be much higher than that in the cylindrical conductor. In most circumstances, electric current flows in a closed path, which we call a circuit. In a simple circuit, current I has same magnitude everywhere. The electric current equals the rate at which charge crosses any plane perpendicular to its flow. This depends on 4 factors. They are the number of carriers per unit volume, cross-sectional area, charge on each carrier, and average carrier speed. Consider once again the water in a pipe analogy. The water pressure in the pipe will be analogous to the electrical potential. But the difference is that in the case of water in a pipe, we can measure the pressure at any point. But in the case of electrical potential, we can measure only the difference in potential between 2 values. For example, at x is equal to 0 and x. It is given by delta phi equals phi x minus phi 0. Phi x is the potential at x and phi 0 is the potential at x is equal to 0. We can speak of anodic current and cathodic current. Anodic current generated by species, that is anions, diffusing towards anode. Now cathodic current is represented by IC and it is generated by those species, that is cations, diffusing towards cathode. By definition, anode is always being a site of oxidation and a cathode is a site of reduction. In the same way, expresses anodic current density and cathodic current density. One difficulty with the electrochemistry is that the sign conventions are rather confusing. The mathematical signs of current and potentials measured at the anode and cathode depend on the type of electrochemical cells that we consider. There are two basic classifications. Cells are either galvanic or electrolytic. In galvanic cells, spontaneous reactions produce current. For example, batteries. In electrolytic cells, current or potential is applied to derive chemical reaction. Conventionally, current is plotted on the y-axis and a potential is plotted on the x-axis. Look at the following figure. The graphical representation of combined current voltage plots are known as voltammograms. And here we use IUPAC conventions. In the figure, the upper right portion represents an electrolytic cell and the working electrode acts as an anode. In the lower left, that also represents an electrolytic cell where the working electrode is cathodic. And if we consider the galvanic cells, so upper left is for galvanic cell, that is the working electrode will be anodic, then potential difference is negative. Now the lower right, that is for galvanic cell, the working electrode is cathodic and the cell is galvanic. Another concept we have to study is the exchange current density, small I0. As mentioned earlier, equilibria exist at an interface between conducting phases, but these are dynamic in nature. Every second, a certain number of charges cross the interface in one direction and an equal number of charges cross over the other direction. Thus, even though the overall current is zero, partial current constantly crosses the interface in both directions, and we observe an exchange of charged particles between the two phases. At the junctions between electronic conductors and electrolytes, the exchange is associated with anodic and cathodic partial reactions. When these two reactions occur at the same extent, an equilibrium is established. The rate of exchange of charge is called the exchange current, capital I0. When we refer this to unit area of the interface, it is the exchange current density represented by small I0 or lowercase I0. For the electrode mentioned earlier, there will be no net flow of current because the electrode process is at equilibrium. Then the electrode is said to be non-polarized. On the other hand, if the electrode process is not at equilibrium, a net current flow will occur and the electrode is said to be polarized. Now, the deviation of electrode or cell potential from its equilibrium value is called overpotential or overvoltage. It is defined as eta equals E minus E equilibrium. It can be either positive or negative. When we say potential, we actually mean potential difference. We usually use delta E or delta phi to represent potential difference. For a non-spontaneous cell reaction to occur, an overpotential must be applied. The extent to which the reaction is driven beyond the equilibrium potential is given by E minus E equilibrium. For example, let us calculate the overpotential required to deposit platinum 2+ from a solution. Just ignore ion concentration and a rate of deposition. Suppose that a voltage of 2 volt is needed. For platinum, the equilibrium potential is 1.2 volts. Therefore, the overpotential is 2 minus 1.2, that is equal to 0.8 volt for the deposition of platinum. Now let us think about the consequence of the existence of overpotential. In an electrolytic cell, the existence of overpotential implies that the cell requires more energy than thermodynamically expected to drive a reaction. But in a galvanic cell, the existence of overpotential means less energy is required than thermodynamics predicts. In each case, the extra or missing energy is lost as heat. Generally, we may consider 3 types of overpotentials. One is the activation overpotential. If in a reaction the electron transfer is slow, such reactions will have high activation energy. For such reactions to occur at a reasonable rate, significant increase of applied potential over the equilibrium value is necessary. This excess potential is known as activation overpotential. Second one is the resistance overpotential. It is also known as ohmic overpotential. Resistance overpotential generally arises from the passage of electric current through an electrolyte solution surrounding the electrode. Third one is the concentration overpotential. It arises due to concentration changes induced in the vicinity of the electrodes by electrochemical reactions occurring there. Now let us consider another type of overpotential. It is called a bubble overpotential. It is a specific form of concentration overpotential and is due to the evolution of gas at either the anode or cathode. This evolution of gas reduces the effective area for current and increases the total current density. The figure simply shows formation of bubbles at an electrode. It has been observed that the bubble overvoltage is independent of pH for many cathodes. But in strongly acidic or alkaline solutions, deviations sometimes occur. Since overvoltage is due to a slow stage in the ionic discharge process, increase of temperature will decrease it. As a general rule, the change is roughly 2 mV per degree. Now let us examine the different stages in the reaction at a cathode in an aqueous solution containing hydrogen ions. The first process will be the transfer and diffusion of H3O+ ions to the electrode layer. H+ remains as H3O plus ions in solution. Next is the transfer of these ions or protons to the cathode. After that, neutralization of the charge of the ions or protons occurs by electrons. Then the combination of resulting hydrogen atoms to form molecules. Finally, evolution of hydrogen molecules as gas bubbles. The essential factor in overpotential is stage 5, that is the gas bubble formation. This is because overpotential is related to the gas bubble formation. Tafel proposed stage 4 as the rate determining stage for overvoltage. This is because at this stage the combination of hydrogen atoms occur to form hydrogen molecules. According to this theory, the high electrode potential, which shows itself as overpotential, is due to the accumulation of hydrogen atoms at the cathode. The variation of overpotential from one metal to another is because of their differing catalytic efficiency for the reaction. The low overvoltage metals such as platinum, palladium, nickel and copper should be good catalysts for the reaction. Two hydrogen atoms giving hydrogen molecule. On the other hand, those of high overvoltage, example lead, mercury, tin, cadmium, etc., are expected to be poor catalysts. Further, low overvoltage metals are best catalysts for hydrogenation process. If the electrode surface is thinly covered with atomic hydrogen, the rate of the reaction 2H giving H2 will be proportional to n square. Here n is the number of adsorbed hydrogen atoms per square centimeter of the surface. Now, the potential E of an atomic hydrogen electrode, neglecting activity influences, can be represented as E equals RT by F ln n plus a constant term. That is equation 1. The constant term depends on hydrogen ion concentration of the solution. The potential of an atomic hydrogen electrode corresponding to the reversible hydrogen potential is E0, and E0 is RT by ln n0 plus a constant. Here n0 is the number of hydrogen atoms per square centimeter of the electrode surface in equilibrium with normal hydrogen gas at a 1 atmosphere pressure. If we subtract equation 2 from 1, we get the difference between E and E0. It is nothing but the overvoltage or overpotential. Thus, eta equals RT by F ln n by n0. Equation 3. Equation 3 does not contain any constant terms. Thus, according to the Tafel theory, the overvoltage should be independent of hydrogen ion concentration. This is in general agreement with experimental values. We have studied earlier that I is equal to Kn square, where I is the current density and K is a constant. Therefore, we can write N as square root of I by K. Substituting for N in equation 3, equation 3 is eta equals RT by F ln n by n0. We get eta equals RT by F ln I raised to half divided by K raised to half into n0. And upon simplification, we have RT by 2F ln I minus RT by 2F ln K n0. Now we write minus RT by 2F ln K0 as E, which is a constant. That is, eta equals RT by 2F ln I plus A. Or we may write a more simplified form as eta equals A plus B log I. And this is the Tafel equation. This equation is an equation for a straight line. Therefore, a plot of eta against log I should be a straight line. And it is observed that the straight line is obtained only at a high field region. The slope of the graph is B. B means 2.303 RT by 2F. If you find out the numerical value, it is 0.29 at ordinary temperatures. Now let us pass on to the main topic of our discussion, the Butler-Volmer equation. It is one of the most fundamental relationships in the study of the rate of electrochemical processes or electrochemical kinetics. It describes how electric current on an electrode depends on the electrode potential. Considering that both cathodic and anodic reactions can occur at the same electrode, that we have already seen. Consider a metal-ion electrode. Probably it is the simplest electrode that we can have. For example, a silver rod dipped in silver nitrate solution. Again, the simplest possible electrode reaction that we consider here is a one-step, one-electron transfer reaction. For example, M plus ion plus electron reversibly giving M. That is equation 1. Even in reactions involving two electrons, only one electron is transferred in the rate determining step. Now we have to find out whether this process takes place by itself or is driven by some force. To know that, we check whether the chemical potential of the species M plus are the same on either side of the interface. That is, here on the electrode and here in the solution. At the instant of immersing the electrode into the electrolyte solution, the chemical potential of the species may not be the same on either side. Hence, there may not be an equilibrium at the interface. This will be a driving force, and as a result of it, the reaction takes place spontaneously. In fact, the essence of electrode reaction is its interfacial electron transfer. Once again, look at the figure. Here, as the arrow shows, the current is from the solution to the electrode. The current can be considered as either the flow of positive ions across the interface in the same direction as that of the current, or the flow of electrons in the opposite direction. These two flows are formally equivalent. Now look at the diagram. At the top of the figure, an electrode and an electrolyte solution are shown. Consider the movement of a positive ion or an oxidized species towards the electrode. The graph shown below gives the potential energy possessed by the ion at different distances from the electrode. We assume that the ions start from the outer Helmholtz plane, move across a small distance in the double layer. As the ion moves, its potential energy varies. Each point on this diagram represents the energy corresponding to a certain location of the moving ion. At this point, the potential energy of the ion is this much. Here, this is the value. It varies, so on. Somewhere along this way, the electron transfer occurs from electrode to the ion. At present, we are not concerned about how the electron is transferred to the ion. Actually, electrons tunnel from the electrode to the ions at the interface. The occurrence of charge transfer reaction is represented by the motion of the point from an initial state to a final state. Look at the picture. The positive ion has to climb over a potential energy barrier. Therefore, it must have a certain amount of activation energy before the charge transfer is attained. Remember, at this stage, we are still considering the first instant of introduction of the electrode into the solution. At this instant, no electric field is acting on the ion. That is a zero field situation. Then the rate constant of the forward reaction, that is reduction, could be written using the Ehring activated complex theory. It is given as equation 2. Kf equals Kt by h e raised to minus delta G0 Zf double dagger divided by RT. Here Kf is taken as the rate constant for the forward reaction. That is of the equation 1. And K is the Boltzmann constant. And here double dagger is a typographical symbol like asterisk. Delta G0 Zf double dagger is the standard Gibbs energy of activation for climbing the energy barrier when there is zero electric field acting on the ion in motion. This happens only at the instant of immersing of the electrode. Kt by h is the pre-exponential factor. We can rewrite equation 1 in a more generalized way. That is, here OX is the oxidized species. For example, M plus or Fe3 plus. Red is the reduced species. That is, M or Fe2 plus, etc. Using the rate law, the rate of the forward reaction will be the product of rate constant and concentration of oxidized species. We can see later that the process is first order. Therefore, we can write rate as K into concentration of reactant species. That is, RF is the rate of the forward reaction equals Kt by h e raised to minus delta G0 Zf double dagger by RT into concentration of the oxidized species. Here it is the electronation or reduction process is taking place. That is the cathodic process. Equation 4 can be written in a more simplified way as RF equals Kf into concentration of oxidized species. Kf is the rate constant for the forward reaction under zero field. It is given by equation 2. Up to this point, there is only chemistry and no electrochemistry is there. Even though the system is under zero field, electron transfer reaction occurs and the interface may not be at equilibrium. Due to the migration of electrons from the electrode to the acceptor ion, that is M plus ion, there is an increase of positive charge occurs on the electrode. Similarly, an increase of negative charge occurs in the solution side. Thus, both sides of the metal solution interface become charged. This leads to the formation of a potential difference across the metal solution interface. We represent this potential difference as delta phi. Thus, the zero field situation changes. This happens within microseconds as the electrode is introduced into the electrolyte solution. When the electrode is more positive than the solution, delta phi is greater than 0. Hence, there will be a potential gradient. It could be like this. Delta phi will be maximum at the electrode solution interface, and it is almost equal to 0 in the bulk of the solution, that is near the outer Helmholtz plane. Therefore, electrical work is required to move the positive ion up the potential gradient. Thus, the activation Gibbs energy is increased. The electric field at the interface activate the positive ion and do electrostatic work on it. But here we need only a fraction or part of the potential difference for activating the ion. The other part will be utilized for the de-electronization process, which also is taking place simultaneously. We will come to that soon. This fraction is determined by a term called a transfer coefficient or symmetry factor. It is usually represented by alpha. Its value varies between 0 and 1. When the transition state is more near to the oxidized species, like this, the Gibbs energy for activation is almost unchanged, and alpha may be 0. When it resembles the reduced species, alpha is almost 1. Generally, we take the value of alpha as half, so the peak will be at the midpoint. Therefore, if we consider 1 mole of the ion, the electrical work needed is alpha delta phi F, where F is the Faraday. Thus, the Gibbs energy for the ion to electrode transfer is increased by alpha delta F, that is the forward reaction, which is cathodic. Thus, the total Gibbs energy of activation will be the sum of the zero field Gibbs energy and the electrical contribution, that is alpha delta phi F. Thus, for the forward reaction, you know that it is reduction and it is cathodic. Delta G F0 double dagger is equal to delta G ZF0 double dagger plus alpha delta phi F. Here again, ZF means zero field. Delta G F0 double dagger is the new activation energy. For the backward reaction, that is oxidation, which is anodic, the positive ion go downhill the potential gradient. So Gibbs energy is reduced by an amount 1 minus alpha into delta phi F. Thus, the total Gibbs energy of activation will be the difference of the zero field Gibbs energy and the electrical contribution. Here the electrical contribution is 1 minus delta into delta phi F. So, delta GB0 double dagger is equal to delta G0 ZF double dagger minus 1 minus alpha into delta phi F. Here delta GB0 double dagger is the Gibbs energy change, that is the new Gibbs energy change for the backward reaction. Now the rate of forward reaction, that is cathodic, including the electrical contribution, can be written as RF is equal to kT by H e raised to minus delta G0 F double dagger by RT into concentration of oxidized species. Writing delta G0 F double dagger in the expanded way or as given by equation 6, we can write Rf equals kT by h e raised to minus delta G0 Zf double dagger by RT into e raised to minus alpha delta F by RT into concentration of the oxidized species. This equation could be simplified further by writing Rf equals Kf into concentration of oxidized species multiplied by e raised to minus alpha delta phi F by RT. That is equation 7. It represents the rate of forward or cathodic reaction. It is the number of moles of positive ion reacting per second by crossing unit area of the interface. When this quantity is multiplied by the charge per mole of positive charges, that is Faraday, we obtain the electronation current density. Electronation means reduction, or therefore we say that the cathodic current density IC. IC is equal to F into Kf into concentration of oxidized species multiplied by e raised to minus alpha delta phi F by RT. That is equation 8. The reaction we took as an example, that is equation 1 or equation 3, which is shown earlier, is reversible. The reverse reaction is the removal of electrons or de-electronation. So far we were discussing the forward reaction. And a forward reaction is electronation or reduction. That is a cathodic process. And now we consider the opposite, that is a de-electronation or oxidation, and that is the anodic process. In the de-electronation reaction, the electrical work of activation is minus 1 minus alpha into delta phi F. Therefore, we can write an equation for the rate of de-electronation similar to that of equation 7. Here we consider the backward reaction or anodic reaction. For the anodic reaction or the backward reaction, the new Gibbs energy is delta Gb 0 double dagger equal to delta G Zf0 double dagger minus 1 minus alpha into delta phi F. And here B indicates backward, that is the anodic process. Therefore, the rate of the backward process Rb could be written as Rb equals Kb into concentration of reduced species multiplied by e raised to 1 minus alpha delta phi F by RT. And let it be equation number 9. Now the de-electronation current density Ia could be written in the same form as IC. That is Ia equals F into Kb into concentration of reduced species into e raised to 1 minus alpha delta phi by RT. Here Kb is the rate constant for the backward reaction. And note this as equation 10. The forward reaction we considered is electronation reaction. This makes the metal electrode more positive because electrons are withdrawn from it. At the same time, the backward reaction, that is de-electronation, opposes this by supplying electrons to the electrode. When there is no external electric field, both processes become equal and opposite, and at some value of delta phi, the electrode's rate of loss of electrons and its gain of electrons become equal. The potential is then represented as delta E. E means equilibrium. That is, the forward and backward reactions come to an equilibrium. Under this condition, the cathodic current density IC will be equal to the anodic current density IA. So, no net current will be flowing. But at the same time, both electronation and de-electronation processes are taking place in the opposite directions at the same rate. That is, these two processes are taking place at equal rate. Hence, a dynamic equilibrium occurs. Under this situation, we get equation 11. In equation 11, we equate the expressions for IC and IA. Once again, I remind you that the explanations given so far is based on the instant at which we dip the electrode into the electrolyte solution. It is only a short duration of the order of microseconds. As I said earlier, delta phi E is the potential difference across the interface at equilibrium. Thus, at equilibrium, both cathodic and anodic current densities could be represented by the same terms given by equation 11. The magnitude of it is represented by I0. It is called the equilibrium exchange current density. That is, I0 equals IC equals IA. And this happens only at equilibrium. That is, the anodic and cathodic processes are taking place at the same rate. This equilibrium situation can be removed by applying a potential difference delta phi across the interface by connecting to an external potential source. Because of the applied potential difference, the electronation and de-electronation processes occur to different extents, and a net current I is produced. It is defined by the following sign convention. The net current I is equal to IA minus IC. That is, anodic minus cathodic. Other sign conventions are also there. The difference between applied potential and the equilibrium potential is called the overpotential eta. Eta is given by equation 13. That is, eta equals delta phi minus delta phi E. Now we write down the net current I as equation 14. That is, we subtract cathodic current density from anodic current density. The exponential terms outside the brackets arise due to the applied overpotential eta. This term is for the anodic process and this term is for the cathodic process. Now the terms within the brackets are same by equation 11. That is, both the terms within the brackets are equal to I0. Therefore, we can rewrite equation 14 by taking I0 outside. Hence, we get the final equation I equals I0 within brackets e raised to 1 minus alpha f eta by RT minus e raised to minus alpha f eta by RT. This equation we write as equation number 15. Equation 15 is our equation, that is the Butler-Volmer equation. It shows how the current density across a metal solution interface depends on the overpotential eta, which is the difference between the actual non-equilibrium and equilibrium potential differences. Small changes in eta produce large changes in I, that is current. The variation in current with variation in overpotential at particular exchange current density can be represented graphically as shown here. In the graph, the right upper quadrant represents the net anodic process and the lower left quadrant represents the net cathodic process. In the lower part, current is negative, and in the upper part, it is positive. And this is in accordance with the IUPAC convention. When I is very small, we get the first graph. Here the variation of current with potential is very little. For the second graph, I0 is small. The third graph is at large I0, and the fourth one is obtained at very high I0 values. For many reactions, alpha is equal to half, and for many others, alpha is remarkably close to half. The curves shown in the figure are for alpha is equal to half for several values of exchange current density I0. It is apparent that if I0 is small, a large value of eta is required to produce even a small current. If eta is positive, the net current density I will be positive and have net anodic current. Then the cations flow away from the electrode. On the other hand, if eta is negative, the net current density I will be negative, and we have a net cathodic current. The cations flow towards the electrode. At the midpoint, I is equal to 0, eta is equal to 0, and delta phi is equal to delta phi E. We shall now consider two special cases of the Butler-Volmer equation. One at low overpotentials and two at high overpotentials. Let us take the first case where eta is very small. When eta is very small, the exponential terms within the bracket of equation 15 will be very small. So we can use the following approximation for exponential terms. That is, e raised to x is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial plus etc. approximately equal to 1 plus x when x is small. Applying this approximation to both the terms within the brackets of equation 15, we get equation 16. The simplified form of 16 is I equals I0 into f eta by RT. According to equation 16, the current density is directly proportional to overpotential when the overpotential is small. This means that there is a linear relationship between current density and overpotential. That is, the graph will be a straight line in this region. That is, when eta is very small. In the second case, we consider comparatively high values for eta. And usually, eta is taken as greater than or equal to 0.12 volt. In this case, the second term of the Butler-Volmer equation, that is e raised to minus alpha f eta by RT, can be neglected. Therefore, we have I is approximately equal to I0 into e raised to 1 minus alpha f eta by RT. Let it be equation 17. Taking logarithm of equation 17, we get ln I is equal to ln I0 plus 1 minus alpha f by RT into eta. And let it be equation 18. And equation 18 is an equation for a straight line. That means we can plot ln I against eta, which will be a straight line with a slope 1 minus alpha f by RT. So we get a graph like this. The graph shows good agreement with the experimental values, especially when overpotential is comparatively higher. For lower values, it deviates. We can write equation 18 in another way. We can separate eta as eta equals 2.303 RT by 1 minus alpha f log I minus 2.303 RT by 1 minus alpha into log I0. The second term can be taken as a constant. We take minus 2.303 RT by 1 minus alpha into f log I0 as a small a. So the above equation could be written in a simple form as eta equals b log I plus a. Let it be equation 19. And here we use the absolute value of I. In this equation, both b and a are constants. B is taken as 2.303 RT by 1 minus alpha f. Equation 19 is in the same form as the Tafel equation, which we have seen earlier. Actually, both 18 and 19 are Tafel equations. So far we have studied some basic topics of electrochemistry, and also we derived the Tafel and the Butler-Volmer equations. Thus, Tafel equation is applicable at comparatively higher overpotentials. With this, I am concluding this session. Hope that you got an idea about Butler-Volmer and Tafel equations. For more videos like this, subscribe my channel. Also share the videos if you like it. Thank you.